Okay, we'll go ahead and get started with the next presentation, but before we dive into the profilers, I really do want to caution you that when you're trying to port code to a GPU, that you spend a little time getting your code cleaned and check for all the errors in it. It's really frustrating when you get a different answer on the GPU and you spend 3-4 days tracking it down and you realize that you've got uninitialized memory or a memory error on the CPU. And so your answer on the CPU wasn't correct and you're trying to reproduce it on a GPU. You waste a lot of time doing that. You should get about the same answer on a GPU that you do on this. So one of the techniques that we've used is to have our CPU kernel run it, and then bring the data back from the GPU and compare them. And there'll be a slight drift in the number, the round off, because the compiler generates slightly different code, but they should be almost the same. And so that's one of the techniques we use to port a file or loop, one loop at a time. And that's very effective because it tells you which loop is getting the wrong answer. It is tedious, but it is probably one of the better ways. Because then when you move from AMD to NVIDIA and you're getting different answers, you know what loop it is. So let's go ahead into the Rocprofv3, which is our basic profiler. So right now, it's gone through quite a few revisions, so we call it Rocprofv3. So Rocprofv3 gives you basic profiling. I still recommend Rocprofv3 before you jump into the other tools. These tools that we're going to be talking about, this is what usually people want the most information in our presentations, because it's harder to understand the tools and learn how to use them than, let's say, a compiler. And they keep changing. So, you know, if you know how to run it from a year ago, that may not be the same as how you run it today. There's just continual change. So let's look at our three GPU profiling tools. There's others that are used on the CPU, but these are for the GPU. And we have Rocprofv3 here. And Rocprofv Compute will use a lot of the information from Rocprofv. And Rocprofv3 we'll talk about next, but that is a higher level tool. So what is Rocprofv3? It's basically collects data from the hardware counters. So we can get hardware counters from the GPU. Now, hardware counters are designed for our hardware engineers. And this is true on a CPU or a GPU. They may not mean what you think they mean, because they're not intended for us, for the hardware designers. And I have seen where authors of 3 different tools would run their tools on the same kernel and get three different outputs, because they're all using the data differently. So don't be surprised if the numbers aren't exactly what you think they are. Especially in the memory cache system. What do we count as a cache load? What do we count as a use of a vector register? It may just be passing through there because the compiler needs an extra register. So all of these now are built on this profiler software development kit library. And the tools are changing a lot because they're trying to make them more robust and use a common interface for all of them to get information from. And so a couple of these tools, Rocprofv Compute and Rocprofv3, came out of our research group. And all of a sudden there was such a demand for them because they were so useful. They said, you're going to make this production. And so they had to take out all their hard-coded stuff that they had for the MI200 and support all the other GPUs as well. So lots of changes on the profiling tools. We're going to talk about Rocprofv3 right now. And this is very quick to use because it's a command line tool primarily. And it will give you the key information generally that you need to understand what's going on. So it's going to show you the top few kernels that are taking up runtime. It's only looking at the GPU. So it's going to give you a list, an ordered list of the ones that are taking the most time. There is some good documentation on how to use it. So with a single process, you use the double hyphen to just before your application, and then the arguments of the application come after that. We have a bunch of options on what information to collect. So here we're going to get a runtime grade. We can run it with MPI run, but it's not really giving you information about MPI. We use Rocprofv3 for that. The different trace modes that you have over here, you can select what information you're getting. As a starting point, I would suggest doing systrace. That may give you, if you're finding that gives you too much information, you may want to use something that's just showing a small subset of all the data. So we can also add this option of stats. That's going to give us a file, a CSV file with statistics about all the kernels, or the top kernels, I should say. And here we're seeing an output from that. So I believe this is the summary that we get with this option here. We also get the CSV file of, it shows you the top 5 kernels. And generally that's enough to know what we need to work on next. So we see here our Jacobi kernel is taking most of the time. And you can probably look at the top 3 and not worry about the rest at this point. We'll go into a deeper analysis. That's sometimes what's showing up as your top kernel may not be the one that you can do much about. So we're collecting hardware counters. There are a lot of them, a lot of different hardware counters you can collect. You can give it a list of them. Like any hardware counter profiler, it can only collect so many each run. So you see this PMC line, and then a list of the hardware counters it's going to count for that run, and then it's going to do a second run here and get more counters. And then it tries to make sense of them, combining them to tell you what's going on. And then we're going to get a file out, a CSV, common separated values. And you can put that in a spreadsheet or just read it, the text on your terminal. So it's going to give you one line per kernel invocation. So we usually want to have it add all the values, collect them all for each kernel and just show one value for the kernel. There's a pretty detailed exercises in the exercise document, page 96. And if you want to work through those, the first example is a Tsukuba example. And I do strongly recommend running these profilers because it is difficult to do this on your own program if you haven't gone through the simple example.
Bob, this is Chung-Han. Shall I ask one more question about the profilers, the GPU profiler?
Please do.
Yeah. Normally, we can decide the profiling for the profilers. That we can decide the sampling for the profilers. GPU profiler also provides such kind of a sampling ratio. For example, the 100 millisecond or the microsecond level. As you know, sometimes it's the overhead depends on the sampling ratio. It's possible to such kind of the functionality for the GPU profiler.
Didn't quite understand the question.
My question point is that CPU profiler provide the sampling ratio. We can determine the sampling ratio. For example, what we just gather the hardware registers or the instructions for 100 millisecond level. For example, we can change it the 10 millisecond or the 1 second, such kind of things. In my understanding, the overhead, the profiler will be changed the sampling ratio. And then I'm just curious about the GPU profiler provides such kind of functionality or not.
It should be similar to the CPU profiler. It will take quite a bit longer to run the GPU hardware collection, just like on the CPU, but it's going to show you the real time as close to what it thinks is the real time that it will take to run those kernels. So it's going to show you that information.
Okay, yeah, thank you. Thanks so much.
I think the hardest thing with the hardware counters is to know which counters you should be collecting, because there's so many of them. The default ones are pretty good for most applications to start with. But you may want to look through all the counters to see if there's others that may be valuable for your workload. So the first file that you will get out will show every time the kernel is called. But if you collect the stats for, let's say, hip trace, and they've been adding more and more stats files for different trace options. So here you're going to see the hip API stats, and it's going to collect all the calls to hip memcopy, and it's going to report that here. All the calls to memset, and showing these in the order, in the total duration of each of the calls in sorted order. So here, what is this telling us from this output on the Tsukuba run? It's basically telling us that a lot of our time is spent in mem copies and mem sets. That we have stream synchronize is taking a lot of time. And so we would start trying to reduce some of those things that are taking time to get our code to run faster. These are just the HIP calls. If we do this, if we add other options, we're going to start seeing things like the kernel times. So as we see in this next step, where are the kernels? Well, we didn't ask for them. So now we add kernel trace. We see the kernel time. So now we see the Jacobi iterations here. So we're starting to see what's taking the most time in running in the compute part of the operations on the GPU. And the ones we want to first look at, the Jacobi iteration is not surprising to be one of the ones that are taking the most time, but we can look at that and try to optimize it. Well, one of the things you might find very interesting is we had a couple questions about that HIP example in MPI. Although I think we may want to wait for Rocprofv3 to look at that, the HIP versus the OpenMP. What I really wanted to do was to look at those 3 transpose examples. What kind of data do you get out for those? If you can start understanding why they're slower when we don't have coalesced loads. We did add an option, I believe, in the latest version that it will generate traces for Vampire, but Vampire is a commercial tool, but you may find that useful for the traces. Here we have some exercises for OpenMP.
Well, what would be like a drop-in replacement workflow or drop-in workflow for something like Valgrind? When you want to focus on memory peaks and things like this.
Okay, so there was a question here. What is a drop-in replacement for Valgrind? So
Yes.
Valgrind is a memory correctness tool, and it's pretty heavily used on the CPU side. I actually recommended it for 20 years ago for DOE to fund it to support MPI. So it also works with MPI, but the developer, I think, has stepped away. It's a tool called Dr. Memory that you may also want to take a look at. It's supposed to be faster than Valgrind, but Valgrind is still heavily used. But on the GPU side, LLVM has a bunch of tools, and they're labeled ASAN, address sanitizers. They have a bunch of sanitizer tools, and the address sanitizer does what on the GPU side. And it supported particular versions of operating system. So it's a little more difficult to use on the GPU, but I would run the memory tools on the CPU first, try to clean up everything there, and then run the tool on the GPU to catch anything which is showing up there. Yeah, Valgrind, it's 25 years ago, we were able to catch an error where the memory was being allocated in C and the uninitialized memory was being flagged in Fortran. And Valgrind was able to find it. Race detection. Intel, I believe it's Intel Inspector is the best way. Yeah, use the Intel tool set for that. They have Intel Inspector and Intel Advisor, I think. My memory serves me right, but we used to use that to catch the race condition. There are other race condition tools. The really neat one that I recommended for for an award on and it does a static analysis of the code and finds race conditions. Let me see if I can pull that one up. Really pretty amazing, but it isn't seem to be as supported as well as it used to be. Well, this is a Medium article on the Codirect tool to find race conditions. And normally for race conditions, you have to have unit tests, and it only shows you the race conditions for the code paths you have in your testing. Codirect does static analysis and flags a lot more things, like even in vector code. So it's and so Ignacio from Lawrence Livermore was one of the key developers of this, and you may want to take a look at that. It's moved around a lot, so some of the websites are not up to date. So here's the sample report from it. And I think it's integrated with Git now as a continuous integration tool. And race conditions are really, really hard to find.
When you say static, what like it?
So normally to get a race condition, you have to have a unit test that passes through that section of code. This one is basically doing the analysis like a compile.
It just
Yeah.
it just looks at the code logic and
Yeah.
Okay.
Yeah. Because if you're not exercising the code
Yeah.
in the dynamic analysis
Yeah.
tools, you're not going to see the race condition. So it's actually pretty amazing tool that they can do that. Valgrind also has a tool associated with it that does race conditions, but it has a lot of false positives that kind of makes it frustrating to use.
Oh, yeah, there's a GitHub action for it, so you can just integrate this UI.
One of the problems with tools and tool developers is somebody will do it as a graduate student project or something, and then they get a real job and the tool disappears, or the funding disappears for them to continue development of the tool. And so tools are underappreciated and underfunded, underused, because they take some time to learn. And in my book on parallel and high performance computing, chapter 17 just lists all the tools that you might want to take a look at, because a lot of people don't know about all the tools. Okay, so we're going to start a little early on the Rocprofv3, and I want to spend a little more time on it than we have in the agenda.